Great honor to be here to present our work today. My name is Qinghui Zhang from Beijing Technology and Business University in China. The title of the paper is GEMvis, a visual analysis method for the compression and refinement of graph embedding models. We are going to talk about it in detail according to this outline. And now, let's start with the introduction part. As we all know, graph data is a vital data structure, such as social networks, word co-occurrence networks, and communication networks. They are widely present in a variety of real-life applications. Thus, graph analysis provides insight into social structures and so on. And therefore, graph analysis have been the focus of academic research. But graph data volume are always very large, so we often use graph embedding technique to help with graph analysis. Graph embedding is the technique for representing graph information by using a set of computable low-dimensional dense vectors. These sets of embedding vectors are constructed by some graph embedding models, that is, GEM represents graph embedding model. The input of graph embedding model is graph data, including the set of vertices and the set of edges between vertices, and it outputs the embedding vectors. A graph embedding model should preserve as much as possible the structural features of corresponding nodes in the original graph. Typical graph embedding models include deep work, node-to-vec, struct-to-vec, SDNE, and so on. Each graph embedding model has slightly different retention capabilities. We found that graph embedding models often cannot retain both local and global structural information, and it is difficult to interpret the output of the model. Therefore, it is necessary to select the appropriate graph embedding model for the graph analysis task effectively and to optimize the ability of the graph embedding model. Firstly, it is needed to acquire how to evaluate graph embedding models. The methods of link reconstruction, node classification, and visualization-based are recently available for evaluating graph embedding models. However, link reconstruction-based method requires a great deal of computational effort to confirm the structural information of input data. Node classification-based methods are usually related to the node labels, and the results of a visualization-based approach is still ambiguous. Using visualization technique is an effective solution to evaluate and compare graph embedding models, and most visualization techniques tend to apply dimensionality reduction technique for comparing graph embedding models. Existing methods mainly refine graph embedding models by tuning the parameters in three aspects, such as graph sampling method, neural network structure, and loss function. However, graph embedding models have a complex structure with hyperparameters, so the refinement results cannot be seen in real time after parameter adjustment. In summary, existing evaluation metrics is difficult to evaluate the ability of graph embedding models to return specific metrics. Secondly, existing methods of comparing graph embedding models are insufficient qualitatively analysis dimensionality. In addition, it's hard to observe the graph embedding models' refinement results in real time after parameter adjustment. In this paper, we present a visual analysis system called GEMvis, and the main contribution includes a series of metrics, R-known metrics, an interactive visual compression approach to support the understanding and the compression of graph embedding models, a tuning mechanism for the neural network-based graph embedding model, and the visual analysis system GEMvis. Finally, 3 case studies are given to illustrate the effectiveness of GEMvis. Then, the background of our work and design requirements will be presented at length. In this paper, we researched the NN-based GEM. NN-based GEM represents graph embedding models which consist of neural network structure. We take deep work as an example to explain. Its work principle is shown in figure. Firstly, NN-based GEM will vectorize the graph data. Secondly, it will calculate the expected output of neural network. Then, NN-based GEM will update neural network parameters interactively by using loss function. Finally, if the interaction gets the stop situation, the model stops training and outputs embedding results. It can be seen that NN-based graph embedding model mainly consists of three parts, such as graph sampling, neural network, and loss function. Node centrality metrics are often used to quantitatively characterize node structure in a graph, so we choose the following 9 node metrics, such as the degree. It is the number of links connected to the node. In a graph, the larger the degree is, the more neighbors the node has. These 9 node metrics can determine the node's relative importance and measure the graph structural features quantitatively. Based on the above knowledge, it can be seen the task of graph analysis is focused on how to effectively evaluate, compare, and refine graph embedding models. Thus, we developed the following design requirements. Firstly, we require GEMvis can support users to qualitatively evaluate and compare graph embedding models' ability to preserve topological features of original graph. Secondly, it needs to support to perform interactive relation analysis among multiple views. Thirdly, it needs to support to quantitatively evaluate and compare graph embedding models' ability. Finally, it should support users to interactively train graph embedding models and save the training results. Then, GEMvis approach will be present at length. GEMvis is designed to help compare and refine graph embedding models. The system comprises a data processor and a visual analyzer. The data processor mainly calculates the node metric of original graph, the embedding result, and the return capability of graph embedding models for each node metric. The visual analysis mainly represents the data processor results, interactively comparing and refining graph embedding models. Let's turn to the data processing section first. Inspired by the working principle of an NN-based graph embedding model, we normalize the 4 typical NN-based graph embedding model into 3 parts, including graph sampling, neural network, and loss function. The default values of the parameters for the 4 GEMs are shown in this table. With the purpose of quantitatively measuring graph embedding model's ability to preserve structural features, we propose an indicator R node matrix to evaluate graph embedding model's ability to return node metrics. It is calculated as the following steps. The first step is predicting the node metric values of embedding vectors by using the NN-based regression model. Then, calculating R node metrics by the coefficient of determination. As can be seen, the closer the value of R node matrix is to 1, the better the capability of graph embedding models to return the specific node matrix. Note that indicator R node metric only describes the retention capability of graph embedding models for 1 node metric. Therefore, the 9 R node metrics involved in this study requires repeating the above steps 9 times. After training, 9 R node metrics are obtained, which can quantify the retention capability of graph embedding models, noted as R degree, R closeness, and so on. In order to compare and refine the graph embedding model, we designed GEMvis. The visual interface of GEMvis consists parameter panel, node metric, original graph, embedding result, R node matrix, and historical record views. To clearly explain our approach, the open dataset CSPHD is used in this study. This dataset contains the relationship between PhD students and their supervisors in computer science. It contains 366 nodes and 735 edges. Case 1 illustrates how to quantitatively compare two graph embedding models. For example, when user needs to evaluate and compare the retention capability of deep work and structured work, he needs to choose deep work and structured work in the parameter panel. After training, the R-node matrix will quantitatively show the retention capability of the original graph structure features for the two models. In this view, the two glyphs shows 9 R-node matrix values of deep work and structured work, where the red one represents deep works and the green one represents structured works. Obviously, deep work takes a higher value than structured work on the R closeness axis. Hence, deep work has a better ability to retain the closeness node matrix than structured work. In addition, the trained graph embedding models parameter values and their R-node matrix values are saved by the system and displayed in the historical records view. Case 2 illustrates how to qualitatively compare two GEMs. For example, when user need to evaluate and compare the retention capability of deep work and structured work, he can browse the closed clusters in the embedding results view by deep work, and the corresponding nodes in the node metric and the original graph views are highlighted, and the other nodes are faded. Then, turning on the color switch in the parameter panel and brush all nodes from top to bottom on the closeness axis in the node matrix view. As the closeness values of nodes decrease, the color of nodes change gradually from red to green. It can be seen deep work has a better reaching capability than structured work in the closeness matrix from qualitatively aspect. According to the above view analysis, it is known deep work with default parameters values has poor retain capability for degree, page rank, and leverage cent. If the user tries to refine deep work's this matrix by GEMvis, firstly, it is need to choose the deep work with default parameters as a baseline and have it compared the retain capability of deep work with tuned parameters. Secondly, in the parameter panel, the tuned deep work named deep work 2 can be set neural network input as the adjacent matrix activation function as sigmoid and local structural as 1. After training, it can be found in the R-node matrix view. The value of R degree, R page rank, and R leverage cent in tuned deep work are significantly higher than those in deep work with default parameters values. So, in conclusion, we present GEMvis, the visual analysis system for the interactive and interpretable compression and refinement of GEMs. In GEMvis, a new indicator R-node metric is proposed for measuring the ability of graph embedding models to return specific node metrics. A multi-view collaborative approach based on interaction and color mapping is provided to support in-depth observation and analysis of embedding results from the original graph, node metric, embedding result, and R-node matrix view. An interactive refining mechanism is provided for supporting users to improve graph embedding model ability to preserve specific node metrics by adjusting parameters in the 3 components, including graphic sampling, neural network, and loss function. However, several aspects of the system can still be improved. First, we plan to expand it with the additional node metrics to characterize the graph, so that more R-node metrics can be applied to more accurately measure graph embedding models' ability to preserve graph structural features. Second, we also plan to include more graph embedding models in the system. In addition, we will provide more in-depth interpretability of graph embedding models. That's all. Thank you.